illustrious, which has significant feedback. When I say feedback, I really mean this recycling, throwing gas out of galaxies, and a similar simulation, but just that does not have these galactic winds. So what we see in this first comparison is the angular momentum at the first time that gas falls into this galaxy, it becomes star forming, versus the angular momentum at the accretion time onto the halo. And what we find is that in both cases there is suppression. Gas loses angular momentum as it does this part of its journey, but when no feedback, no winds are included in the simulation, somehow this loss is stronger, and we don't really understand yet why that is. Moving on to the next phase, now we are comparing the angular momentum that gas has at this point, at the last time that it's becoming part of the galaxy, versus the angular momentum we had at this point. So the angular momentum changed during this recycling through the fountain phase. And what we see is that in the simulation where there are strong winds, there is some gain of angular momentum during this cycle. While in the simulation which doesn't have those winds, there's essentially not much change. And finally, we can compare the angular momentum that gas has at the time that it is converted into stars versus the time when it just joined the disk for the last time. And again, in the simulation without feedback, we actually see a conservation of angular momentum overall in this phase, but there is loss of angular momentum in the disk when there is no feedback in the simulation. So we combine all these things together, and we overall see, compare the angular momentum at redshift 0 versus the angular momentum at the accretion time onto the halo. And again, we see that the inclusion of feedback significantly suppresses the loss of angular momentum during this nonlinear phase, but there's still some offset. And you can see this here in the summary plot as a function of time, these events, the relative change in the modulus of the angular momentum. Without feedback, we have this consistent loss, but with feedback, we have some smaller loss and gain through the galactic fountain, and then conservation of the angular momentum. So this is what happens in what we find in the nonlinear phase. We can compare this to a plot we've seen earlier of the modulus of the angular momentum as a function of cosmic time for the dark matter in black here. So here we see the linear phase, it grows exactly as we expect from theory. Then at some point around redshift 3, the turnaround time, it stops growing and stays constant in physical units for the dark matter, while for the stars, for what will end up as stars, we see that around the same time, entering the nonlinear phase, there is some loss of angular momentum. It's the same thing that we see here. Now, we can also look at the reorientation angle over the cosmic time. So remember, I already described that there is some angle between the angular momentum in the initial phase and in the final halo. So again, we see this for the dark matter, where around the same time that we go into the non-linear phase, decoupling from the overall growth, there is some reorientation of the direction in which the angular momentum points. This is more significant for the stars. So let's go a little bit in more detail into this change of direction and how well essentially can the linear theory predict the direction of angular momentum for nonlinear objects. So what's shown here is this cosine angle distributions of the angles between the initial and the final time for dark matter in black, and for the stellar component, baryons that will eventually become stars, in green. So we see that for high J galaxies, so these are kind of essentially disk galaxies, there is some around 20 degrees reorientation that we've already seen before. This is true also for the stellar component. While for galaxies ending up with low angular momentum, so elliptical galaxies, for the stellar component, it becomes much more closer to being uniform distribution. So there is a significant decoupling of the direction of the angular momentum between the initial and the final time. Let's look at an example just to get a feeling for what this looks like. So actually I'm going to take here bit of an outlier example. This is a galaxy that in the final time is a nice disk galaxy. Nevertheless, we will see that it has significant reorientation of its angular momentum over cosmic time. So what we see here is dark matter and gas for the components that will end up in at redshift 0 within the halo or within the galaxy. Okay, so both of these things will be spheres in the end. Now we see them at very high redshift of 100 or so, and the lines here show the direction of the angular momentum. So we see that in the initial time, in this case, they're pretty well aligned. There's also only a 10-degree difference in the initial conditions between these two components. And we let them play over time. We see the collapse. And for most of cosmic time, so we see that the red here shows is fixed, shows the direction in the initial conditions, while the blue shows it as a function of time. Early at pretty low redshift, and now we see that really at very late times there is a significant reorientation of the angular momentum of these baryons. So to emphasize, these particles are the same particles throughout this movie. We don't add anything. At very late time, there was something that flipped the disk by about 90 degrees. Okay, so after we went through these different phases in the evolution, let's look at what this looks like for in the end, at redshift 0, for the relation between the angular momentum of gas and or of stars and dark matter. So this is shown here. Again, these cosine angle distributions in blue. We see that for high angular momentum galaxies, at the final time, they are aligned with their the angular momentum of the full dark matter halo by about 16 degrees, while low J galaxies have much larger misalignment between the stars and the halo. For comparison, in red, we see these distributions in the initial time, in the initial conditions. And what I want to leave as a puzzle for the next few slides, and we'll get back to this, is how come in the end the final misalignment between dark matter and baryons is very similar to the initial one, in spite of the fact that we see some significant reorientation over cosmic time. Before getting back to this puzzle, I want to look spatially what this looks like. What does this correlation between stars and angular momentum and dark matter angular momentum look like as radially resolved? So what we see for high J galaxies, there is local, very good alignment between stars and dark matter, with angles between just a few degrees around the disk radius and 10 or 20 degrees or so. And then when we look at the angle between the galaxy and the enclosed dark matter as a function of radius, we get a very similar profile. This is because the dark matter itself is very well aligned in different shells, in galaxies that end up as disk galaxies there. So the local misalignment and the global misalignment are very similar. In contrast, for low angular momentum galaxies, we see, again, pretty reasonable local alignment. So in any shell you take, the dark matter and the stars have about 30 degrees between them. But then when you look at the galaxy and the overall halo, this goes up to this 52 degrees that we've seen here. This is because the dark matter itself has larger twisting in galaxies that end up as low J galaxies. And we see this, the dark matter twisting itself that varies on galaxy, depends on galaxy morphology. That was for the angle. Now if we look at the modulus, we see that after all these changes, all this loss and increase of angular momentum over cosmic time, we indeed end up with a really weak correlation between the modulus of the stellar angular momentum and the dark matter angular momentum at the final time, Pearson coefficient of just 0.14. But if we look at the dark matter modulus within the galaxy radius, so in the inner part of the halo, we get a much better correlation. So there's something, all these changes that the baryons go through, somehow they're also related to the inner halo. And I think this has to do more with the selection, with this angular momentum bias. Even with all of these changes, the baryons ending up in the galaxy are more related in the initial conditions to what ends up as the inner part of the halo than the halo as a whole. And this correlation even remains when we're looking at the inner part of the halo in the dark matter only simulation. So it's still the inner part of the halo in the dark matter only simulation still tells us something more than the halo as a whole about where the galaxy forming will be, how the galaxy forming will correlate. Okay, and with all of these changes and reorientations and so on that we've seen, question that may come up is how deterministic is all of this? To what degree can we model this accurately with all of these changes? And for that, I want to introduce a very particular set of simulations that can tell us about that. So what you see here are two identical galaxies from simulation, that cosmological simulation that was evolved down to redshift 5. So these are galaxies of redshift 5. And then what I've done is stopped the simulation, copied it to a new directory, changed one bit in the position of every particle in this one simulation, and then reran the original simulation unchanged, and this simulation where I changed one bit in the position of the. So this is like 10 to the minus 7 parsec perturbation. So this moving is going to show the evolution of the system over cosmic time. On here on the right, show just two measures of angular momentum. One is the angle between the galaxy and the halo angular momentum, and on the x-axis just the modulus of the angular momentum of the galaxy. You can already see these 2 points, red and blue circle, are not identical, but maybe at this point you still cannot tell by eye that these galaxies are different, so let's give it a little bit more time, and while you're watching